Well, good morning. Today we're going to look at probably the last aspect of vectors we haven't seen yet, and that is the cross product. It's another form of multiplication that is genuinely unique to vectors. And as we had seen with the dot product, where it could be considered a projection of the x component of one vector, the magnitude of the vector, onto another vector. This is the sign projection of one vector onto the other, and we'll take a look at that. The thing about vectors that is unique is that unlike the dot product, where you end up with a scalar in the end, which is just a number, you end up with another vector. And so, and this vector happens to be normal or perpendicular to the plane of the two or three, depending on how many vectors you've got, vector planes that are created. So that is a property also that can be utilized. But let's take a look at the cross product. It can be quite confusing in a way because it's quite different from the dot product, where you only multiply like terms. For example, the y components only get multiplied and the x components only get multiplied. Only those that have normal vectors that are the same get multiplied. Here, only the vectors that are not the same get multiplied. And this is how we do it. Now I'll show you. But first we'll take a look at an important aspect, and I think what may help us with this cross product, a certain aspect of cross product that's essential to know. It There is a little rule that is applied to this that can help us in obtaining the correct vector outcome. It's called the right-hand rule. So what we'll do is we'll first get this adjusted to the screen, and we'll take a look at vectors. Okay, so let's say we'll work with 2 dimensions at this point. Well, actually, it'll be 3 in a way. So we have x, let's see, the XYZ coordinate system. And y. Okay, so we got a break here. Okay, we call this the x, negative x, z, and y, that's negative y. And we have little unit vectors, I, j, k. the magnitude of the unit vector again is 1. To simplify things, it makes vectors easy to understand because it assigns direction. So when we do a cross product, we have a vector, let's say A, that is AI plus BJ, and we have a vector B whose CI plus DJ. The cross product, boy, having trouble with this. A cross, and that's how it's denoted. It looks like a regular multiplication sign, and X cross B. Now, we only multiply opposite or different vector components. We can't, unlike the dot product, where the dot product would be A dot B would equal to AC plus BD, and that's a scalar. Here, the similar I cross I equals 0. So AC I cross I equals 0. So you can't, the same similar components, vector components, yield 0. So we have A D I cross J, and we have to remember one thing: the order of the cross product is important, and we'll look at it in a second. And in this case, we have, okay, so we looked at A cross I, AI cross CI is 0, AI cross DJ, AI cross, DJ, yields a real component. Now we look at B. B, C, J cross I. Remember, the order makes a difference. B, where J cross J is equal to 0. B, D, J cross J equals 0. So this is all we're left. And it turns out that I cross J is K. So you can see this is the plane that I cross J, if we had a line across there. This is the plane, the XY plane. And you could see that AD K, it's normal to that plane. And plus BC, now we have, instead of I cross J, we have J cross I, which happens to be negative K. So we have to put negative K here. So this is equal to AD minus BC in the K direction. So we end up another vector whose magnitude is A times D minus B times C in the K direction. So we have another vector D. We will say cross B is equal to D, which is equal to this vector in the k direction. Now let's take a look at how we got that result. Okay, so we're given a rule where we have I cross J, and it's called the right hand rule. So you use your right hand and you turn from I into J, and your thumb, which direction your thumb is the direction of the resulting vector. So I dot J is K. J cross I is downward. You see my thumb's downward. So J cross I is negative K. If we have J cross K, you could see that as I curl my palm from J into K, my thumb goes in the I direction. So J cross K is equal to I. It's called the right hand rule. And conversely, K cross J is equal to negative I. So position counts in the cross product, which is very strange. It's much different than any kind of multiplication that you would assume. Now, K cross, or some people call curl, K curl I is in the J direction. So K cross I is equal to J. And notice that it's always something different from it's perpendicular. They're always perpendicular to the components in the cross product. So the KJ plane, which is the ZY plane, let's say if you thought of this as a window frame and you got a pane of glass being held by this ZY frame, that's the ZY plane. And the JK is in that plane. I is perpendicular. It comes out of that ZY plane. So you could see that these always yield vectors that are perpendicular to that plane. But remember, the right-hand rule gives the direction. If you don't get the order correctly, you'll have the wrong answer because the resulting vector would be pointing in the wrong direction. In fact, in the opposite direction. So here we have I cross K equals negative J. And then we have I cross I, J cross J, and K cross K equals 0. So you never get any contribution from like components of vectors. So you can see that there's a little bit more involved in the cross product. The cross product is kind of a difficult, it's more difficult, let's say, than a dot product. So let's take a look at let's take a simple look at something here. We have vectors A and B, and let's say we have vector A. Let's make a two-dimensional situation here for a second. We're going to have a vector plane. And we're going to have vectors A and vector B. And A. And we've got an angle here, theta, and an angle here, phi. And this is something we did before. This is x, this is y, and we can make believe a z component is coming out of the board. Okay, so I cross j, if we had unit vectors j and I cross j would come out of the board like that. So we have vectors A and B, where A is simply AI plus BJ, and vector B is equal CI plus DJ. Okay, and now we have A cross B. So we go A cross B. Well, what if we did that on the magnitudes of A and B? So that would be equal to A on A squared plus B squared I plus B on A squared plus B squared J cross we'll make a bigger bracket. Okay, cross C on C squared plus D squared I plus D on C squared plus D squared J. All right, but we realize that this is, for A, the cosine of theta plus phi I plus sine of theta plus phi j cross, this is the cosine of phi I plus sine phi j for B. This is a j, sorry. Boy, that's a lousy J. Here we go. And we'll bracket that. Okay, like components are zero. Remember, I cross I equals 0, J cross J equals 0. So we have in this case cosine equals, whoops, why these pens are so directional. Cosine of theta plus phi times sine phi I cross J plus, all right, well, we can't cross product the J components, so we have sine theta plus phi cosine phi J cross I. Well, J cross I is just the negative, so we have cosine of theta plus phi sine phi k minus sine theta plus phi cos phi k. So they're both in the k direction. Now, but this is negative k. This is negative k. This little j cross I. And I cross j is k. See, I cross j comes out of the board, and the opposite goes into the board. So now all we have to do is apply our trigonometric identities, and we have an interesting result. We end up with, all right, this is going to be, I hope I can write it, cosine theta cos phi sine phi minus cos phi, whoops, sorry, this is sine theta sine phi squared, and everything's in the k direction, so minus, this is sine theta cos phi sine, or cos squared phi minus sine phi cos phi cos theta k. Now, this term and this term are opposite, and so they cancel out. And we have negative sine times sine squared minus sine times cosine phi squared. So we end up with minus sine theta times cos squared phi plus sine squared phi, and we know what that is. That's 1 in the k direction. So the answer to this is, this whole business is minus sine theta. minus sine theta k direction. We'll make a k hat so that it looks that way. So we have a vector that's coming out of the board. So we have our identity here, A cross B equals the magnitude of A times the magnitude of B times the sine theta negative and the k direction. So this is an identity. This is a two-dimensional. We're going to generalize if we have, let's say, a vector that's in the x, y, z. A has x has I, j, k components, and B has I, j, and k components. Then this generalizes to a vector n that's normal to the plane of these two vectors. So that's a cross product for you. Like I promised, it was a little more difficult than a dot product, but it is very useful because in science, the cross product is used for many different things, especially where, let's say, forces come into play that um, are normal to one another or in different directions. You want to know what direction the resulting force is going to be in and what the magnitude of that force is going to be. It gives you a very useful insight. If you know the material, let's say you're constructing a bridge, and you want to know what the forces are. Let's say this bridge is a suspension bridge, and these are the towers that support it. And you want to know you got a force in this direction, force in this direction, and force in this direction. And you got forces like wind that come at it this way. You want to know what that wind, let's say the wind is going, let's say, into the board in that direction. You want to know if it has any components that it's going to add, any additional stress that it's going to add in this direction or whatever direction. Is it going to lift? So there are different things that that cross products give insight into that are very, very useful. So let's take a look at a little more complicated vector. Let's say we have A is equal to 3 I plus 4j minus 3k. And b is equal to 2i plus 3j plus 2k. What's the A cross B? Cross B in this situation? Well, we got to look at it component by component. So we have A cross B is equal to 3i plus 4j plus minus 3k cross 2i plus 3j plus 2k. I always like to draw a little vector diagram to help me understand which direction I'm supposed to assign in my cross products. So this is I, this is j, and this is k. And remember, I cross I is 0, so we have 3 equals 3 times 3 I cross j, and 3 times 2 I cross k. Okay, that's one component. Now we have the j component. So remember, j cross j is 0. So we have plus 4 times 2 j cross I. Remember, the order is very important. You don't lose that order in cross products. Okay, 4 j times 2k. So we have plus 4 times 2 j cross k. And we're not done yet. We got our last component. We have minus 3 times 2 k cross I, k cross I, and the last one is minus 3 times 2, or minus 3 times 3, I don't have any room here, k cross j. Okay, so we have 9, I cross j. I cross j is k, plus 6, I cross k. Now, I cross k is in the negative j direction, so that's negative j. Okay, this is plus 8, j cross I. Again, j cross I is in the negative direction, so that's negative k. And we have plus 8 j cross k, which is in the positive I direction. J cross k. And here we got minus 6 k cross I. That's in the positive j direction. J. And 9, that's minus 9, k cross j. So k cross j is in the minus I direction. So we got minus I. Now we add up all the similar components. Okay, so I is in the first, so we got 9, 9 plus 8, I. So that component and that component is out. Okay, now we have the j direction. Okay, in the j direction we have minus 6, minus 6. That's negative 12 in the j direction. Plus, now we got rid of our j's. In the k direction we have 9 minus 8, k. And let's make this understandable. So that's 17i minus 12j. Whoops, I wrote another I, sorry. Minus 12j and plus k. That's our resulting vector. So that's how you do a cross product. And it, as you can see, it can become tedious. People during the 19th century invented linear algebra with matrices, and they made columns, for i's and j's and k's. And they used to perform certain operations with these matrices. They called it linear algebra, but it helped with vectors. It helped with the calculation of cross products and vectors. And you may run into that in some occasions. It's linear algebra is a topic in its own right. It's somewhat complex. They do teach it to some extent in college um, for engineers who are going to be doing systems of simultaneous equations where you need to find a common solution to 3 or 4 different equations. And matrices come in help handy there and trying to solve those types of equations. But linear algebra is kind of a awkward mathematics itself because it's very cumbersome stepwise. The number of, let's say, to find the determinant of a 4 by 4 matrix is not so straightforward. So now we've seen all the different aspects of vector math. We've seen scalar products, we've seen dot products, now we've seen cross products. And let's take a look at a couple of problems now. All right, so let's do another cross product. And hopefully, if we do it right, we can demonstrate that it's normal to the plane. Okay, and again, we have vectors A and vectors B and B, and between them we got an angle, and they form a plane. Okay, and if we do a cross product, we will find a vector that's normal to that plane, that is perpendicular to that plane. So let's take a look at, let's say, A is equal to 2i plus 3j plus k, and b equals, I'm just pulling this out of the air. I plus 2j minus k. All right, so A cross B is equal to 2I plus 3j plus k cross I plus 2j minus k. All right, so I and I is 0, 2 times 2, I cross j, okay, and minus 1 times 2, I cross k. Okay, now this is a j. Sorry about that. Okay, 3 plus 3 times 1, j cross I, and minus 3, or plus 3 times minus 1, j cross k. And finally, we do the k's plus, all right, 1 times 1, k cross k, k cross I, and we have 2 times 1, k cross j, so plus 2, k cross j. All right, and again, we draw our little I, j, k. Okay, I cross j is k, so that's 4k. I cross k is minus j, but that's a minus, so that's plus. Well, we'll just see how it can get complicated. Minus 2 times minus j. All right, so I curl j, or k. 3 times 1 plus 3 times 1 is 3. J cross I, so that's a minus k. Minus k. And we have a plus a minus 3. J cross k, that's in the I direction. Plus k cross I is j. J. And plus 2, k cross j, that's the minus I direction, minus I. So let's get all of this straightened out. So we have, let's look at the I components. So we have minus 3 and minus 2, so that's minus 5. I minus 2 minus 3. Now j's, we got plus 2 plus 1 is 3 in the j direction. So we got rid of our j's. And k's, now we got 4 minus 3 is 1 plus k. All right, that's our resultant. So if this is normal, then this result dot A should be 0. So A, let's call this D. A dot D is equal to 2I plus 3j plus k dot minus 5I plus 3j plus k. So this is equal to minus 10 plus 9 plus 1, and that's equal to 0. So we did it right. And it is normal. Remember, any vector that is normal to the plane of other vectors, the dot product will be 0. So we do indeed, this vector that we got is normal to the plane of A and B. So that worked out very nicely. Now let's take a look at this dot B. And let's take a look at this. We don't need all of this anymore. I think the important thing is being very fastidious about the order of the cross product and getting the curls right. You know, the direction of your vectors correct. So let's say B dot D is equal to I plus 2j minus k dot minus 5I plus 3j plus k. And let's see what that comes out to be. And that's equal to minus 5 plus 6 minus 1. So that's 0. So there you go. It's normal to the plane created by vectors A and B. So this is D. And it's normal to our vectors. Actually, it would be at this point. So our D wouldn't be there. And it would be in the K direction. And this is D. That's how it would look. So that pretty much encompasses vector mathematics. And we do have a number of problems that we can take a look at. Let's see if there's anything that right at the moment looks interesting. Just a minute. We looked at the normal projection, cross products. Try to build vector C with other vectors. No, I don't see anything that's really going to be insightful into our, let's see, equation of a line. I don't see that as being particularly interesting. You know what I'll do? I'm going to cut the video at this point. Well, here's the law of sines. Derivation of the law of cosines using vectors. That could be interesting. We may, you know what we'll do in the law of sines using vectors. You know what we'll do is we'll I'll take a little look at this further and we'll do some more problems. Here's a force problem. It tells you what the forces are. These are sort of engineering problems. And here's a torque problem. You know what we'll do is I'll review these problems and we will take a look. Here's the proof of the Pythagorean theorem in 3 dimensions. Yeah, so what we'll do is take a look at some of these problems in the next video. So we've looked at all of the critical aspects of vector math, okay? And we will take a look at some problems in the next, I think interesting problems too, in the next video. So I'm going to brush up on some of those problems, work through them so that we can go through them without disruption, and we'll finish up vectors with that. And then we'll start into stuff that's really pretty interesting. I may just throw in a little bit of linear algebra just so that you have a taste for it. But we're not going to focus much on linear algebra. I'm pretty much set on beginning with some of the fundamental calculus ideas. We're going to start with derivatives and move into integration, and then we'll take it from there. But yeah, I think from this point on, it's going to get pretty interesting. So anyway, this is Mathman wishing you well, and again, if you have any questions, leave them in the comments section, or if you have a comment to leave, just leave a question. If you have a problem you want solved, leave it in the comments section, and I'll try and do my best to help. So anyway, this is Mathman wishing you all so long.